Hello guys, today we are going to discuss one of the exciting paper on the GAN called StarGAN. The paper full name is Unified Generative Adversarial Networks for Multi-Domain Image-to-Image Translation by 𝐀𝐻𝐨𝐿 and his team. So this paper is interesting results. Like if you see this figure, like its names is already mentioned, like multi-domain image-to-image translation. And if you see this figure, like here is the one input, like the person face, and they transfer this person face into different domains. For example, here the hair color is changing as a blonde hair. Here gender is changing, like male to female. Here is age is changing, this person is, and the here is pale skin is changing, and this translation is in the different domain. And this is the example of the celib A dataset, and this is the example of the RAFT dataset. For example, here is the input person face, and here is the output of the persons on the different facial expression. For example, here is angry, here is happy, here is fearful. So StarGAN, in this paper we see how this StarGAN helps to achieve on these results, and what is the benefit of the StarGAN in compared to the others previous work. So let's get started. So here is the abstract. Like the main focus of this StarGAN is like there are the different works related to this multi-domain image-to-image translation are done, but the main problem in that is, since different models should be built independently for every pair of image domains. So what is meant by that is, like if you have the input image and if we are translate to this bold here domain, then we need the separate domain to translate from input to bold here, and input to gender, input to age, input to pale skin, and so on. So every pair of image to image translation needs one generator. But for example, if you see the cycle GAN, then there is the one image domain and there is another image domain, and for every translation they need one model, one generator discriminator. But StarGAN proposes the one novel architectures that perform image to image translation for multiple domains using a single model. That is the one benefit and the exciting work of this StarGAN paper by this author 𝐀𝐻𝐨𝐿. So they propose like the unified model architecture of the StarGAN that allows to simultaneously transform from one image domain to another image domain without changing anything. I mean, there is the single model, shared generator, and they transform these input image to these other translation domains simultaneously. So it is like the exciting idea. Let's see how this StarGAN achieved. So for example, the main in abstract, what they are saying is like in the previous work, for example, this domain A blonde hair to domain B brown hair, or the domain E blonde hair to domain C gray hair, and so on. They need separate generator. For example, A to B, they need generator A to B. From A to C, they need generator A to C, and so on. So it is like the quite of like the boring task, right? And they also mention like if you in such models, the problem is like they don't know how to correlate. For example, this domain A and translating to black hair, and or the domain A to translating to domain C, they are not correlated to each others, and that results something, the bad result in this data set. For example, this RAFT data set, for example, there is the input, and if you have to translate to angry, and at the same time if you have to happy, and if you train the models on the separate models, then they don't know how to correlate between this expression to this expression. So the output may not seem to be natural, and we will see the result how they compare to the baseline models later on. So the main concept is they propose the shared generator instead of these separate generator from translating one image domain to another image domain. So it is most clarified from this figure. For example, translating if you have the mapping for the k domains, then we need k times k minus 1 generators. In this, because we have to translate among the 4 domains, right? So we need 4 times 4 minus 1 equals 2 generators. So for example, if we are translate 1 to 2, then generator 1 to 2 is needed, and again if we have to translate 2 to 1, then generator 2 to 1 is needed. So these 2 generators are needed and they are trained separately, right? So obviously if we can common sense, then much error and not good output seems to be produced by this architecture. So what the StarGAN do is like they propose the shared generator, and you can easily translate from one domain to another domain simultaneously. For example, 1 to 3 or 2 to 4 or 3 to 5 simultaneously, so that we do not need separate generator for each of the domain, translating domain. So another, let's say how they do, I mean, for example, this translating 1 to 3 or 2 to 4, how they do, I mean, how this shared generator know how I have to translate 1 to 3, not 1 to 4, how this generator know. And another important thing is they train in the multiple data set, right? For example, RAFT, CVPR data set, and how this model know what data set is training. So they use simple logic. For example, the idea is simple. For example, instead of learning a fixed translation, our generator takes as inputs both image and domain information. Domain is like what domain it have to translate. For example, here there is the input person face, then it have to translate to the blonde here, right? For example, here is in the image, it have to translate the blonde here, and this is the domain information, or it has to translate to the gender, another gender. So it is the domain information. So which domain it had to translate the input, so that is the domain informations. So our generator takes as input both image and domain information and learns to flexibly translate the image into the corresponding domain. So how they do, we use a label, for example binary or one hot factor to represent domain information, right? For example, that can be simple 0 1 or 1 0 to represent the domain, in which domain it want to translate. And another thing is like how the model know, or how the effective approach they are using for joint training between the domains of different dataset by adding marks factor to the domain label, right? There is the two in logic here. One is one hot or binary factor that they use to represent the domain information from in the same dataset, and the models can be trained on the different datasets between domain. Then they use the marks factor to the domain label, and that's the simple idea. But they said like that is the effective approach on these tasks. So it seems like they have the interesting work, right? So if we go detail, then here is like one thing I want to mention is like the discriminator, it has to classify whether the generated image, for example input image to blonde here, then it has to generate like classify whether it is fake, seems to be fake, or real, and at the same time it has to produce some domain information whether it is correctly classified to blonde here or not. That is the more important concept in StarGAN. For example, in discriminator, if we give this input image, and for example generator wants to translate in this domain, that is blonde here, and the discriminator first output is it has to produce whether this blonde here is real or fake, right? That is the similar in all over the GAN. And also they use the concept of AC GAN, that is they also produce the label, that is domain information, whether this input is translated to blonde here or not. Maybe the translate, if we not have this domain class information, then the generator can translate to the gender, for example this domain, but we want this generator to translate to the blonde hair, not to the gender, and that is constrained by these domain class informations. That is the concept of SGAN. We will see later what that is mean. So here is, so for training the discriminator is like we produce give real image and the fake image, and the generator produce the real or fake, that is the generated image, and also the domain classification. For example, whether the generated image is on what domain, I mean what domain generator want to generate, and whether it generate correctly or not. And if we see like the training process or the training mechanism, then just first we provide target domain and the input image to generator, right? But in other words, we can say like we provide the input image condition on the target domain, right? Target domain is denoted by the C in this paper, and we give to the generator, and generator generates the fake image that is condition on the target domain, and it is provided to the discriminator, and discriminator produce whether it is generated image real or fake, and whether it is in which class the generated image seems to be like, right? And it also produce the domain classification, and the back propagations is happening, how the generator is working, the feedback is given, and also the feedback is given to the discriminator, how the discriminator is well on classifying those images, right? And that's how this training works. And if you see like this is the reconstruction phase. For example, why we need reconstructed image in this architecture is like, for example, the generator generates the input image. If you see here, generator generates the input image, and for example it generates to the gender, right? And it produces this image, and discriminator gives the domain classification and the real or fake. But the main thing is like whether the properties like the person is smiling and the eyes or the person appearance is maintained in this figure or not, right? So that is guaranteed by the reconstruction loss, and reconstruction loss is simply like we get the generated output, and this generated output is again goes to the this generated output is again goes to the our generator, given that the fake image condition on the original domain, and it produced this reconstructed image, and we take the reconstruction loss between the input image and the reconstructed image. So why? Because it has to maintain some identities in the original image onto the target image, and that is the main another extra thing they do for the proper output and proper working of the generator, right? So let's see these I gave like the overview architecture and the concept, but let's see in the detail one step at a time. So multi-domain image to image translation. So we have to translate the input image into the output image Y condition on the target domain label C. So that is represented by G X, C produces the generated output Y onto the target domain C, right? We randomly generate the target domain label C, I mean what that is input to the generator, so that generator learns to flexibly translate the input image. So if you see, that is we also introduce like the auxiliary classifier, right? What I already said, that allows a single discriminator to control multiple domains, right? So if there is like here is you can see the single discriminator that controls the multiple domain, that is black, brown, gray, right? This here. So their generator produce this adversarial loss, but at the same time generator produce this domain classification loss. That is the concept of the SGAN or the auxiliary GAN. So that is how discriminator produces probability distribution over both sources and the domain labels, right? That is the sources and the classification. So figure 3 means this figure shows the training architecture, right? So the adversarial loss is similar. For example, the discriminator wants to maximize this loss, and generator want to minimize this loss, right? And where G generates an image G x comma C condition on both input image and the target domain level C, and discriminator tries to distinguish between real and fake. And remember, this D source X is the probability distribution over the sources, right? And the generator G tries to minimize this objective while the discriminator D tries to maximize it. So altogether there are three total loss function used. There is one adversarial loss where discriminator want to maximize it and generator want to minimize it, and they compete as a minimax game, right? And that is the one adversarial loss. And I already said, like, they use the auxiliary classifier GAN. So there is another domain classification loss that is produced by the discriminator, whether the generator generates the fake image, but whether it generates to the targeted domain correctly or not, that is given by the domain classification loss. And domain classification loss of real image is to optimize D, and loss of fake image to optimize G separately, right? There are the two domain classification loss: loss of real image to optimize D and loss of fake image to optimize G separately. What does it means is, like, real classification loss is discriminator learn to classify input X to corresponding domain C dash and want to minimize it. For example, this input image is given to the real image given to the discriminator or the fake image, and it produces the adversarial loss and the domain classification loss, and that is the real classification loss, right? We gave the real image as the input, and this discriminator produce this loss, right? And another is like fake classification loss, generator want to minimize it, that is this. And if you see the D source G x comma C is like the this part is similar to fake classification loss. And for example, input image, that is the real image, given to generator produce the image on target on the domain level, and it is passed to the discriminator, that is the fake image and the real image, and it produces this, right? That is the similar concept of the GAN, right? So I hope that it is easy to understand, and that is given simply as the that is the what is domain classification loss for the real and the fake, right? So I already showed that the reconstruction loss is needed. Why? Because this domain classification loss does not guarantee that the generated image has the same identity information as the input image. So we need extra reconstruction loss, that is the simply absolute difference between the input image and the generated image, right? And don't confuse with the symbol, it is very simple. For example, the input image is there is an input image, and the generator generates the target image or the fake image condition on this domain information C. And again, this is this targeted or generated image is give like the condition on the C dash, that is the original image, right? And the again the generator generates, that is the reconstructed image. What is shown here? For example, generator generates for first input image X, and generator generates the fake image condition on the C, that is target domain, and again it is passed to the generator, same generator, architecture generator, and it condition on the original domain, that is C dash, and it generates the reconstructed image. And we take the the absolute difference between the pixel wise between input image and the generated image or the reconstructed image, that is the reconstruction loss. So the full objective is for the discriminator, there is only the adversarial loss and the real classification loss, and lambda CLS is the parameters, hyperparameters that controls how these classification loss going to affect this real total loss. And the loss of generator is simply sum of the first adversarial loss, right? And there is the fake classification loss and also reconstruction loss, right? And if you see and the main thing is, for the adversarial loss they use the WGAN GP loss, right? So that is the one difference, because in WGAN GP the training is much stable and there is the much convergence, right? So it is it produces the high quality output, so they use the WGAN GP in the adversarial loss. So I already told you this concept. Reconstruction loss is simply an absolute difference of original image X of domain G and reconstructed image by generator on this targeted domain C dash. So so for the implementation is like they said that we use the Wasserstein GAN objective with gradient penalty, that is WGAN GP, and that is the adversarial loss, right? And we use a gradient equals to 10 for all experiments, and I think in the original paper WGAN GP they also set this gradient penalty as a 10. And if we talk about the network architectures, we will see later on. Let's see these architectures and go further forward. So for example, what is the main architecture is like this. This is the architecture used by the StarGAN and the generator. For example, here is the input image X and there is the targeted domain C, right? For example, in which here color want to change, this blonde here, for example, that is the given by the targeted domain C, right? Targeted domain L is the one hot factor. For example, this want to translate on the blonde here, right? This blonde here, and that is the 1 and other are 0, so it is the one hot factor. And input image is 256 by 256 by 3, and the output image is also 256 by 256 by 3, right? So first they use like the encoder types architectures. First they have this pink is denoted by the encoder, and this orange is yellow is denoted by the decoder, right? So the input image axis goes to these two downsampling layer, and then again these three have the ResNet blocks, total 6 have the ResNet blocks, and these 3 are for the encoder and these 3 are for the decoder, right? And it passes to the 6 ResNet blocks, and again there is 2 upsampling layer, and it produces the output as 256 by 256. That is the general architecture for the generator. And this StarGAN is like they propose the shared generator, or the one generator that can generate the multiple domains, and they use like the max factor for which data set it is using and the target domain label. See, for example, generator focus only on the translating this black here to the blonde here, and other translation like the gray, brown are ignored by this model, right? So this target domain, so that this target domain is a one hot factor. And for the different training on the different data set, they use max factor. And we already see this loss function, 3 loss, adversarial loss, domain classification loss. And what does it real classification loss is like, we give the real image to the discriminator, or we train the discriminator first, right? We give the real image, and discriminator is similar architecture, but here is like the downsampling layers, and it produce 2 losses. That is the similar architecture of the AC GAN. First is the adversarial loss, whether it is real or fake, and another is like in which domain it seems like it is the black, right? So that is the training of the generator. So generator, that is real classification loss, and the fake classification is loss is discriminator takes both input, that is the real X and the generated GX on the targeted domain C, and discriminator produce the adversarial loss and the domain classification loss. For example, it is the blonde here, right? That is the fake classification loss. And reconstruction loss is simply for first this input image is passed to the generator, and generator produce this image targeted on the domain C, and it passed to the discriminator outputs adversarial loss and the domain classification loss. And again this input image this generated image is passed to the again back to this generator, but the domain information is the we have to the domain information is CDAS, and generator takes these generated images GX, and try to produce the another image targeted on this CDAS. And the similar architecture, but first it is like the inverted generator. It goes to these two downsampling layers and encoder, and these 3 ResNet blocks for decoder, and again 2 upsampling layer, and produces this image. And we take the reconstruction loss between the original input image and the reconstructed image. And again, why we need is like this domain classification loss not guarantees is like the generated image, like this generated image have the same attributes or the same structures or the look as the input image. And so this reconstruction loss gives constraint to the generator, like it have to change only the here, not the face, right? And so the full objective is like this is the objective, discriminator, and the generator, right? So that is the and for the experiment, if we see, and the one thing is discriminator, they use the patch GAN, right? So why patch GAN? What is patch GAN? Because discriminator takes the patches of the images, not the whole image at a time, right? So the patch GAN have the different advantage, and they are inspired from this StarGAN paper. And I think why they use in here patch GAN is like they want to produce the high quality output, and discriminators takes the input image, and if we see, if the discriminator see patches patch by patch in the image, then it it also see the different details on the generated image, so it helps to improve the generator at the same time. So for the experiment, they use the baseline models as 3 baseline models. That is, the first is diet, second is cycle GAN, third is IC GAN. So again, if you want to go to the diet GAN, cycle GAN, and IC GAN architecture, go to the respective papers and read about it. So I think it is not necessary to understand the architecture here, at least to understand StarGAN. These are the base models they use, and they compare their outputs of these 3 paper, or in these 3 architectures compared to StarGAN. So if you see these on RAFD dataset, for example this, and if we compare these 3 baseline models and the StarGAN, is like StarGAN produces output seems natural, right, on these 7 levels of these these phase emotions. And if you see this cycle GAN, angry seems to be somehow good, but when this on this expression it is blurred, and other seems like the satisfactory, but StarGAN seems more realistic, right? And for example, in this paper here it is low resolutions, and the angry seems seems angry, right? So that is the IC GAN output. So why the main thing is like what author mentioned, like why that is other baseline models is not outputting good, is like they takes the input image, right, and they generates the different emotions. For example, in the cycle GAN, and why this is happening is because this cycle GAN generates this output, but that is not other outputs are not correlated to this angry. For example, fearful is not correlated to the angry, and the models cannot know how to produce the different emotions, but in the natural way or with preserving the same quality. They also mentions for the experiment on the qualitative evaluations, and if you see, if StarGANs have the higher visual quality of translations on the test data to the cross-domain levels. For example, here in this image, if you see StarGAN's output, and here is it is the input image, and there is the domain information on the multiple domains. And if you see, StarGAN have the high quality outputs, because the authors mentioned that this is because the StarGAN's models or architectures provide slight regularizations, because the models launch simultaneously from translating one input image to the multiple domains, and the author mentions that that's why the model launch some regularization effect in compared to the other baseline models. For example, if you see the cycle GAN output, and if this is the here, and if you compare the StarGAN and the cycle GAN, then StarGAN output seems more realistic, right? For example, this, and this is the single attribute transformations, and this is the multiple attribute transformation, right? Height and gender, right? So here and gender, and here and age, both are transformed. Multiple attribute are transformed, gender and age, and height, here gender and age, all three are transformed. So if we compare this on the single domain or the single attributes, then cycle GANs have some satisfactory result, but StarGAN seems more realistic. And if we compare these multiple attribute transformations, then StarGANs have the realistic results, but the cycle GANs not able to generate like the StarGAN. So that is they do qualitative evaluation on the CVPR dataset. So let's go further and see quantitative evaluations. For the quantitative evaluation, they use first they use the Amazon Mechanical Turk to assess to assess the which quality, which network outputs, which architecture output seems to be more realistic. Then like the 66.2% output is for StarGAN on the single attribute transfers, and the multiple attribute transfers StarGANs have the much more than the others architecture, right? So here is a huge difference, right? That is the taken by the Amazon Mechanical Turk perceptual evaluations. So for facial expression synthesis on the RAFT dataset, they set a neutral face as an input, and target domain can be any 7 facial expressions. For example, if we see this, there is the one input image as a neutral image, and the target can be any 7 face expressions, right? And why it seems more realistic on the StarGAN is like StarGAN can correlate between these other domain information, for example sad, surprise, happy, fearful, but this is not the case in the other GAN architecture with the IC GAN, cycle GAN, or the diet. And if you see this IC GAN generates the image, but that is not seems like the preserves the identities on the input image. For example, in the input image there is the girl image, but it generates the different emotions, face emotion, but the output image seems like it is a boy, right? It changes the identity informations, but that is not found in others two baseline architectures, but they are not seems quite realistic. So for quantitative evaluations, again for the facial synthesis, they first trained a pre-trained model or pre-trained classifier with the real input images with facial expression, and then they use that pre-trained classifier to compute the classification error on synthesized image of all the different models as shown in the table 3, where StarGAN has the lowest classification error as a 2.12 in compared to other baseline model, right? For example, why if you see the number of parameters into 14 and only in the StarGAN is 1, because in the cycle GAN we want to transform, there are the 7 face expression, right? And in each face expressions we have to transform from one face expression to another, so altogether we need 14 generators, or 14 models, right? So number of parameters is total parameters is times 14, but in StarGAN it is only 1. So so this is because StarGAN requires only a single generator and the discriminator pair, and regardless of the number of domains, while in the case of cross domains such as cycle GAN, a complete different model should be trained for each source target domain pair. And again, I forgot, like, I want to mention one thing is in these architectures, for example, in these architectures for the reconstructed image, they use the same generator for reconstructed image, right? They don't use the different generator but use the same generator but change this targeted domain and the input. That is one thing I want to add here, and hope that that is more careful, useful. And see, that is the, I think I covered the all the important concept of the paper, and the result are exciting. I mean, this work is all excited resulted here. So I highly recommend go through the paper, and I think, yeah, this figure is more clear. For example, input image and the target domain, right, goes to the generator produce reconstruct image and generate real and the domain classification, for example in CVPR label and the RFFD label. So you if you want to, and here is the detail of the network architecture, how they are using downsampling, how kernels are arranged, how residual blocks are, number of kernels, number of filters, and so on. I think that is the overview of the StarGAN, and I hope that you will understand too. And if you have any questions and any corrections, comments, put down in the comment below, and I will get on the another video of describing another paper. Until then, goodbye, have a good day, bye bye.